CIMNE, and today it's a real pleasure to be able to introduce to you Professor Michael Ortiz, or Miguel Ortiz. Michael is a really well-known professor in the field of computational mechanics. I am sure that most of you will have read his papers and will have studied his work over many decades in the field of computational mechanics. Michael started his studies in Madrid, studying civil engineering, like many of us here, and then went on to Berkeley to do a PhD with Bob Taylor, who again is very well known to many people in CIMNE, and from there on he went on to Brown University, and more recently, in the last 20-odd years, in Caltech, in the California Institute of Technology, which is obviously one of the leading centers in mechanics, in computational mechanics, and in many other fields in science and technology. I think we've all seen the work of Michael over many years, starting in the early days in large strain plasticity, then looking at topics like fracturing and multifactoring of materials, variational time-stepping integrators, data enhancer, model-free technologies, which I think was a very interesting keynote lecture in one of the conferences not many cycles ago. And now Michael is starting to work in a very exciting and new topic in quantum computational mechanics. This is something very new in the community, and Michael and colleagues in Cambridge are probably the people opening groundbreaking or breaking the new ground in these topics. And I think we are very privileged to have him here and delivering a seminar in this area. So over to you, Michael.
Thank you, Javier. Well, after this glowing introduction, you're going to be all very disappointed because what I'm going to present today really is kind of very early days. It's kind of baby steps towards developing an activity in a new field. Okay? And the new field is quantum computational mechanics. So there's been a lot of work in quantum computing, going back to the seminal work of Feynman, for instance. Obviously, there's been a lot of work on computational mechanics. The key is to bring them together. So to look for ways to basically bring quantum computing to bear on computational mechanics, which could be potentially a game changer. Okay. I would like to recognize my collaborators, Borigete Liu and Fekni Chirac from the University of Cambridge. Everything I'm going to present today is from a paper that we wrote together, which just came out. Okay, so that means you don't have to read the paper, just listen. Okay, it'll save you a lot of time. Okay, so for me, this is going back to my childhood. Okay, so I grew up in Lleida, maybe some of you know. So this is the institute where I studied there, the Institute of Science and Media. It's been recently renamed Marius Torres, but I grew up there, and so coming here for me is very nostalgic, and it's extremely thrilling, both from a professional and personal point of view. Let's say it like that. Okay, so what is the lecture plan? Why do we need new computing paradigms? Okay, we have exascale computers. Okay, we just keep using them. Okay, and if you're going to change paradigms, what could be a radically new way of doing computing? And here's where analog computers are kind of staging a comeback, which is, so you can think of a quantum computer really as an analog computer. I'll talk about this in a second. Review of quantum computing, because it's really generally not well known in my community of computational mechanics, so I'll just review the basics so you know what the whole thing's all about. Okay. Now, how do you bring together quantum computing and computational mechanics? That's the key. Do you gain anything really? Is it worth doing? And some examples where we are now in some basic proofs of concept that show that it seems that there is something there. There's really something there. Okay, worth looking into. Okay, and then the outlook in that regard. So basically the theme of the presentation is quantum computing needs computational mechanics. Okay. Well, so first, let me address why new computing paradigms? Why not just declare victory and just keep doing the same thing? But there are many problems in physics and mechanics where really conventional classical computers are really not sufficient. We can really break them very easily. I'll show a very simple example in a second. But so a typical example would be multi-scale computing, where you want to characterize the material behavior by looking at a higher scale of finer and finer scale, so that way you don't have to model plasticity at this level, which is very difficult. You can model plasticity at this level, but it's still difficult. So you go back another level, and still difficult. So you go another level. So you can push him back difficulty to lower and lower, more fundamental scales, and you hope that you'll eventually get to bedrock, where you have simple universal theory, which is parameter free, and that applies to all materials. And that would be quantum mechanics. But you can see that this is a very tall order. There are many scales, and the dream would be to use model-free computational mechanics, in the sense that you get your models from concurrent multi-scale modeling. Okay. So that means doing the macroscopic or the full calculation, and at the same time querying concurrently the behavior of all the material points at a more fundamental level. So, for instance, it's a polycrystal. Okay, that cannot be done today. I mean, that's will be essentially Fe squared, and Fe squared is not really within the realm of feasibility at this time. So classical computing paradigms are bank on Moore's law, the fact that you have exponential growth of the speed of the processors. They're based on binary logic and Boolean algebra. The largest computers at this point deliver exascale performance. I think the largest one is the one at Oak Ridge. Okay, this typical exascale computer with hybrid hardware and so on. And so up to now, from 1993 so to 2021, you see an exponential growth of the performance of classical computers based on binary logic and based on somehow multiprocessing. Okay, I mean, can we continue along this line? And the answer is probably not. Okay, for a number of reasons. So there are physical limits to how much you can meter, how small you can make the basic processors, and we are reaching those physical limits at this point. Power consumption is a huge problem. Nobody talks about this, but the power demands of these computers are huge, and to the point where you really need a dedicated power plant really to feed the computer. There are problems with fault tolerance and failure rates of the processors that you have to mitigate that take away from scaling. So when you look at scaling, very often communication between processors dominates. It's very difficult to get optimal and theoretical scaling. Also challenges with memory, I/O, storage. They're difficult to program, okay, to get good performance on the computers. And the costs are absolutely staggering. Okay, so only maybe the American national labs can afford these kind of computers, and a few other people. Okay, so maybe this is the end point. This is the end of history. It's the end point of classical computing, in the sense that the performance of exascale computers is not enough. You have to try something else. Well, there is another reason. This is a bit of Latin to show that, in Merida, when I was in the institute, we were taught Latin for 2 years, so you can see that I still remember some. Well, so there are some things you just cannot compute with classical computing, because essentially they have combinatorial complexity. Anytime you have combinatorial problem, you're dead. Okay. So just to give a very simple example, a bistable elastic bar, you have a bar, you fix one end, you pull on the other end, you have a number of elements, so much, how many? 1, 2, 3, 4, 12 elements, okay? And perversely, the material in each one of the material points is bistable. So it can be in one phase or another. And the phases, this is the deformation gradient, this is the energy density. The phases are characterized by transformation strengths. Okay, so materials are very clever. They figure out that to minimize their energy, they can combine phases in an optimal way. The question is, what is the optimal combination of phases that delivers the minimum energy? Well, for that, you have to solve this problem. Looks simple. Okay, so the total energy of the bar is the energy of one element. Okay, so this would be the strain in element P. This would be the elastic modulus. And this is the transformation strain that can take one of two values, plus or minus epsilon star. So how many configurations do you have to evaluate to make sure that you get to the absolute minimum energy? And 2 to the n, because you have two possible phases in every element, you have n elements. And let's say that evaluating one configuration, once you fix the transformation strains in every element is order n. Okay, so that we have n, 2 to the n, and that's a staggering number. Okay, so if you have, for instance, 38 elements, it would take an entire exascale computer to do one calculation. 38 elements. A stupid bar, okay, with 38 elements. If you get greedy and you say, no, I want 100 elements, okay, then you get an astronomical number. I mean, this number is unthinkable. It's basically unphysical. So that means that if you are interested in microstructure, okay, problems that have a combinatorial complexity because of their physics, there are limits. There are epistemological limits to what you can learn from a classical computer. To me, I mean, that's the main driver. Okay? But okay, it's a matter of taste. Well, so we have to try something else. How about going back to analog computers? Okay, so after all, a quantum computer is, as we'll see, an analog computer. Okay, that uses quantum mechanics or quantum physics basically to solve other problems. Well, so here you have what is an analog computer. So it's a machine that uses a physical analogy. Okay? So you have a device that you can control that is governed by some physics that are in analogy to other physics that you're interested in. So they were very widely used until digital computers came along. They were wiped out for a number of reasons. They became obsolete in 1950. Here's one of our most famous engineers, Leonardo Torres Quevedo, who was really a pioneer in the development of these analog computers. There, the analogy was to mechanical devices. So he used mechanical devices. This is one of them, which is in the museum of the Escuela de Ingenieros. That he used to solve problems in complex variables, logarithm tables, things like that, things that at the time were important. Okay, so there we have a pioneer, homegrown pioneer. Another typical example that I learned, for instance, as an undergrad, is the membrane analogy. Okay, so you want to solve the Poisson equation with a constant force. Okay, back in the 50s, there were, say, no computers, okay, so you had to do something else. So you used an analogy, you used a membrane analogy. Why? Because the membrane deflection is governed by the Poisson equation. Okay, so any problem that is governed by the Poisson equation is in analogy with a membrane. Okay. And in fact, there are people who've been continuing to develop this technology. These papers from this year, I think. I forgot to put in the, in 2019. And one of the typical applications that I learned as an undergrad was to use the membrane analogy to determine the torsional modulus for cross-section. Because according to Prandtl's theory, here we have Ludwig Prandtl, Okay, so the two are governed by the same equation. Okay, so you have a domain that has the shape of your cross section, would be a y beam, for instance. Okay, that you cannot draw analytically. You put a membrane that spans that domain. You inflate it from one side with constant pressure, and this is basically the solution of the Poisson equation. And the point is that you get the solution instantaneously. You apply the pressure and immediately you have a solution everywhere. Okay, and with infinite resolution. Okay, because the membrane basically is a continuum. Okay, so another example, this I couldn't resist showing because this I actually saw, not these models, but similar models again when it was an undergrad. People didn't have computers where they could do shell analysis. So they really refined the art of building reduced models that would build out of gypsum, for instance, in the lab, and then they would apply different load scenarios and measure displacements and so on. And they would use these reduced models, okay, with a very beautiful math, also scaling relations and everything based on dimensional theory and so on. I mean, they were really, really beautiful. That's an art that was completely lost. I think that it actually, something like this could be back now with 3D printing. When you want to analyze Sagrada Familia, for instance, to build a very detailed 3D printed model, you load it and immediately have a solution. Okay, so it's going back to analog computers because of 3D printing. Anyway, I mean, that may not happen, okay, but the interesting story of this particular model is that they loaded it and it failed, collapsed after a while, but okay. Nevertheless, they went ahead, and this is one of the most beautiful structures, I would say, at least in Spain, that are built from very thin shells. Anyway, okay, so the advantages of analog computers are that they basically entail zero computing time. Okay, so you apply the pressure, you get the solution instantly. Okay, and you get infinite resolution if you want. Okay, because again, the membrane is a continuum. You don't have to discretize it, okay, to find elements or something like that. But of course, they have a number of also disadvantages. So sometimes the analogy is not that clear. Okay, so bring your the physics you're interested in analogy with something else. Sometimes it's not simple. That's the case with quantum computers. We're going to have to work hard to establish an analogy between computational mechanics and quantum computing. This is not so clear. And okay, you require measurement systems and to extract results and so on. So anyway, the question is, if we're going to go back to analog computers, what could be the most general analog computer? Okay, so one that is based on a universal set of physics that underlies everything, basically. And here, of course, we have my late colleague at Caltech, Richard Feynman. This is one of his many, many famous statements that nature isn't classical, damn it. He was not, okay, very, he could be a bit salty. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. You see, he was a man who was attracted to difficult problems, and he left the easy problem for other people. So, okay, so that's basically the idea behind quantum computers. You set up a device that is governed by the laws of quantum mechanics, and you use the very unique properties of these laws to solve problems you cannot compute by classical means. So this IBM's quantum computer, okay, which is accessible to the community. And what a quantum computer does is it takes a vector in a space of very high dimensionality. Now we'll see why. So n is the number of qubits. Then you have 25 qubits. So next year there'll be a quantum computer here in Barcelona with 25 qubits. Okay. So you would be able to encode, in principle, vectors of dimension 2 to the 25. That's a lot. Okay. Now, with 4,400 qubits, in principle, theoretically, you can encode something of dimension 2 to the 433. And again, that's an unfathomable number. Okay, it doesn't work that way exactly, but okay. Under ideal conditions, that would be the case. Okay, and so you have a vector, and on output, you have something that consists of the input vector to which you have applied a matrix that is unitary. So what a quantum computer does generally is it generates or you set up a unitary matrix that you can apply to a vector. And that's what a quantum computer does, and it cannot do anything else. Okay. So either you take your problem and you map it to something like this, or you're done. Okay. Well, so U, as I said, is a unitary matrix, is in the unitary group, okay, which again has dimension 2n. And the these states of the computer are basically probabilities. Okay? You measure each one of the components with the probability that the machine is in that state, okay, and so therefore they have to be normalized to 1. That's another constraint. Okay, so as I said, a quantum computer is a system of quantum particles or qubits and some means to evolve the state. So that would be a unitary operator. Okay, so each elementary bit of information, a qubit, has 2 pure states, up and down. Okay, that could be anything. Okay, so the actual physics of the devices, okay, from which you build the computers can be different. Okay, so could be trapped ions, could be the superconducting cryogenic devices, and so on. But each one of the elements has 2 states, 0 and 1. Okay, but these are quantum states. They're not classical logical bits. Okay, so because they're quantum states, okay, they combine in a tensorial way, not in an additive way. And therefore, if you have n qubits, then the computer, the device will have a total of 2 to the n pure states, okay? And therefore, it supports a vector of dimension 2n, as I said before. We'll see in a, okay, so we can wonder why. So why do you have this tensorial nature? It's really critical. Well, so you may recall from your undergraduate quantum mechanics that really what describes the state of a quantum system is the wave function. So the wave function will be a function defined on configurational space. Configurational space will be typically, for instance, n coordinates of particles or something else. So say that these coordinates are discrete and can take values of 1 to m, because you have a function of n particles that can take values from 1 to m. All the possible values of p define a matrix, okay, that has or an array that has dimension m to the n. That's a function of several variables. That's one way to understand tensorial algebra, right? Functions of several variables that combine tensorially. Now, so say that now these are qubits, so they would have 2 states, so m will be equal to 2. I don't know what I'm doing here. So that gives you the dimension 2 to the n, okay? That's because really the state Q that I showed earlier is really not a vector, it's a discrete wave function, okay? That is a function of a number of variables which are discrete, yeah, and each one of which can have 2 pure states. So this combines tensorially. Well, okay, so this notation is typically not used, so you use Dirac notation, okay, which is you have a vector, this will be the corresponding state, okay. Think of it as a vector if you want. These are just 2 examples. What happens if you have 1 qubit? If you have 1 qubit, so the qubit will have 2 pure states up and down, okay. And then Q0 will be the value of the wave function at 0, and Q1 will be the wave function of the other pure state 1. Okay, and if you have, excuse me, 2 qubits, then you have all these possible pure states. You can have plus plus, I'm sorry, up, 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 down, down, up, down, down. Okay, so 2 to the 2, 4. And these components here, Q0, Q1, Q2, Q3, would be basically the values of the wave function at this state, this state, this state, and that state. Okay, and they have to be normalized to 1, basically. This is the probability that the system be in this state. This is the probability that the system be in the other state, and so on. So this is the basic algebra that you have to get used to. Okay, it takes a little bit getting used to, but there is no way around it because this is what quantum computers do. They cannot do anything else. Okay. Okay, so this is what I just said. Now let's look at propagators. Okay, so you would be just setting up the initial conditions. That would be state preparation, as it's called. But typically, what you want to do is you want to do some calculations. You want to change from an input to an output. This could be force vector, and this could be the displacement, for instance. Okay, and so that is done by applying to the initial conditions again unitary operators, and that's what these computers can do, and that's all they can do. Okay, so just to remind you, unitary matrix is one that its inverse equals its complex summation. Okay, and they define a group, which is a Lie group under multiplication. So you can take these operators, unitary operators, apply them sequentially, and the combination of them is still a unitary operator. So UN is closed under multiplication. Okay, and it's what is known as a Lie group. Okay, it's both a manifold and a group. And the tangent space at the origin is what is called the Lie algebra, and these are the skew Hermitian matrices. Okay, so again, that's the nature of the beast. So computation is performed by evolving the states. Now the point is that once you apply an operator U, it gets applied to the entire system. It's like the membrane. You inflate the membrane, it happens all at once. Okay, so this is sometimes what is called quantum parallelism, and what is the basis for thinking of these computers perhaps as analog computers. Okay, so you can how many unitary operators can you implement? In principle, you can implement any unitary operator. Then we'll see how this helps with computational mechanics. Okay, so far it's just basic stuff about quantum computers. So this is what is called gate logic. You represent your unitary operations as a combination of elementary operations, which are called gates. So these are the typical gates that are usually practiced. These are the Pauli gates. These happen to be a basis for the Lie algebra. Okay, the skew Hermitian matrices that I described, I referred to earlier. This applies the matrix in 2 dimensions as U2. I mean, at least for the special skew symmetric matrices. You see that the trace is equal to 0 in all cases. You get other important matrices by exponentiating these vectors which are in the Lie algebra. You can apply the exponential mapping. You get rotation type operators. There are others like Hadamard and phase. Again, they're used all the time. These are unitary operations that involve only one qubit. Now, that would not be enough because you want to mix up the qubits. You want what is known as entanglement. So you can actually reach the entire dimension of the system. And the fundamental gate that you use for achieving entanglement is the constraint knot gate, which has this metric representation. Okay, so all these gates are in development software kits like QuizKit. Okay, so they're readily available. So you just download QuizKit, okay, and log in, and you have all these at your fingertips. Okay. Okay, so this is an important point that these 2 gates are universal in the sense that you can express any unitary as a combination of these gates. You have a C0 gate that involves 2 qubits at a time, and a rotation gate, general rotation gate, that involves only 1 qubit. And you can take any program, okay, and express it as a sequence of these operations that is called transpiling in the lingo, okay, of quantum computers. And again, it's an operation that is automatically performed by Poisson, for instance. Okay, so, and the importance is that it provides a measure of complexity. So if you want to know, okay, are you really accelerating your computations or not? So there would be a statement about the complexity of the operations. Complexity is very typically measured as the number of elementary gates that you need to express your program. And again, this done by transpiling and then measuring the depth of the program. So it's, later when I talk about complexity, this is the kind of complexity that I'll be talking about, okay, which is standard. Okay, there is one first problem, which is, okay, so say you want to initialize your computation, you want to put a force vector into your quantum computer. It's not so easy, okay? So there are a number of algorithms that achieve that. Okay, so basically, you could encode into a quantum state a vector that has dimension 2n, principal. Okay, and how is that done? So typically, okay, because the quantum computer only can do unitary operations, you have to start from some known state, for instance, the 0 state, and then keep applying elementary operations to it until you get your force vector. Okay, you cannot just read the force vector. Do I 1 to 100 read? No, I mean that doesn't work. Okay, so there are ways of doing this in an exact way, but they're typically costly. That's by a succession of rotations involving 1 or 2 qubits at a time. So I just put here an example. Say you encode this vector. When I encode this vector, you work backwards, take the vector, you hit it by a gate like this, and you get 2 zeros here and 2 numbers there. We don't care about diamond and heart. And then you want to get rid of this, set this to 0 and this to 1. So you apply a rotation gate, and that's what it does. And then the preparation is basically applying these rotations in an inverse way. Okay, the transpose across matrices in an inverse way. This is what is called a circuit diagram. It's just a way of visualizing the operations, the gates. And that's the way you would actually take this vector and put it into the computer. And that's critical because at the end of the day, you want to achieve exponential acceleration for the entire calculation, not just part of the calculation. The entire calculation, it has to give you a logarithmic complexity or exponential scaling. Otherwise, you get bottlenecks and you gain nothing. Okay? So in particular, the operation of introducing a vector into the machine has to be done in a way that ensures a low complexity. Now, that's not the case for in general. So that's the other thing you learn about computers. They are very good for some very special problems, but not for every problem. Okay, so for instance, if the vector is completely unstructured, okay, completely arbitrary, then the operation that I described would have complexity n, and you're dead, because you might as well do classical computers, okay? So you have to bank on the vectors that you use having special structure, okay? They have to be either very sparse, or they should be expressible. So this is a vector you want to prepare. They should be expressible as a polynomial. Okay, this is what is called polynomial scaling. Once you take your vector and you express it this way, then there are very efficient algorithms that allow for preparing these vectors in log n complexity. Okay, this is called polynomial state preparation. So that's always what we do, okay, without getting into further details. Whenever we have a vector that we have to explain to the computer, okay, so here we want you to look at this vector, okay, so we do it by, first of all, approximating it piecewise by Chebyshev polynomials. That's actually an operation that is also on Quiskit. And then apply polynomial state preparation to this representation, okay? And that has to be done for everything you want the computer to be aware of, to make the computer aware of anything. You have to do state preparation. Okay, just to give an example. So let me start with simple examples. Let's say you want to solve string equation, okay, if you want, or the one-dimensional Poisson equation in one interval. So this will be the spatial domain. This will be forcing. This will be the displacement. Okay, say you want to solve this in a quantum computer and see what you can do better than on a classical computer. Well, so we discretize the domain into 2n nodes. Okay, so you have a computer with n qubits. Okay, so BSC has promised a computer with 25 qubits, so you could go all the way up to 2 to the 25 in principle. So, you know, that would be the way you would discretize space. Okay, so into equal intervals. Again, equal is important because you cannot have unstructured meshes. Okay? There's no way. So, as I said, I mean, these computers are very good to solve some problems, but not all problems. You have to have regularity, sparsity, polynomial structure, things like that. Okay. So we want to enforce this force that we encode into the computer. So now the computer knows the force. And we apply the Fourier transform, the discrete Fourier transform. Why? Because it's a unitary operation. So there is a quantum version of the Fourier, the discrete Fourier transform that is very efficient. Oh, wow. Is it something I said? It's very efficient, and you know, it can be implemented in a very efficient way in quantum computing. So most of what we've done has been based on polynomial state preparation and QRT. Okay, so you have this operator which is unitary and easy to implement. And now comes the little bit of a surprise. Okay, you would think you're done, but you're really not. Okay, because if you express the Poisson equation in the Fourier space, oh wow. Well, here you would have 2 pi rk, which is basically k squared, and you have to bring it to the other side. Okay, you know, on a normal computer, that's easy. It's efficient operator. On a quantum computer, it is not that easy. Okay, so doing this operation is not that easy. Why? Why? That's the question. Why is the operation not easy? Okay, because it's not a unitary operation. Okay, this is not a unitary operator applied to the state that would give you this state. So somehow you have to learn how to bend non-unitary operators into unitary operators. Okay, so the discrete Fourier transform, great. Dividing by the making this you can think of a diagonal matrix. This multiplying force vector. That operation is not unitary, and you have to sweat it. Okay. How do you sweat it? Well, okay, so this slide is a bit mathematical if you want, but I'm very proud of it. So I'm going to show you because I think this is when I finally understood how do you actually do Hermitian operations, which are not unitary, obviously, in these computers. So say you have a Hermitian matrix, and if it were real, this would be a symmetric matrix, for instance, stiffness matrix. Stiffness matrix would be our favorite symmetric matrix, and you want to multiply it by a displacement. Okay, not so easy. So because it's not this multiplication is not unitary. So what you do is you enlarge the dimension to twice the dimension principle. Okay, so you take the matrix. Okay, this Hermitian. You define this skew Hermitian matrix now, which is in a space of twice the dimension. Okay, and you also lift the displacement you want to multiply to have q and 0. So these are ancillary qubits that you have to introduce, okay, just to represent these matrices. Okay, these are called ancillary qubits. Well, once you have this, then it's clear what to do because C is in the Lie algebra. Okay, so it's skew Hermitian, so therefore It's in the Lie algebra, and you can apply the exponential mapping, and that gives you a unitary operator. Okay, but is that unitary operator useful? Well, so the way you do it is you introduce a small number here, epsilon. Okay, and you take the limit of epsilon going to 0. And if you go through the algebra, the matrix algebra, applying u to q is equivalent to, gives you to order epsilon. I mean, this should be epsilon, yeah, epsilon squared gives you this. This is exactly what you want. Okay, q, so you're done. This is garbage. This is just throw it away. So how do you throw it away? Okay, you take the one component or the product, because basically you're measuring this one component. Unfortunately, it has for small epsilon, we have a factor of I epsilon, so you divide by I epsilon, you take the limit, and you get exactly the operation. So you get these operations that are not unitary, they're Hermitian, by introducing ancillary qubits. You have a large system. Now, the nice thing about the Poisson operator is that this multiplication, this matrix is diagonal, so you can do it component by component. So you have to introduce only one ancillary qubit, because you're doing this the diagonal matrix, you do it component by component. Okay, and that this would be the solver. Finally, okay, you have the quantum Fourier transform. You have this operator that gives you the multiplication by the diagonal matrix. Okay, then the inverse Fourier transform. No, I'm sorry, it goes this way. I'm going the wrong way. Sorry. First, you have state preparation. You have to take your force and stick it into the computer. Then you do Fourier transform. Then you divide by the diagonal, and then inverse Fourier. You get a solution. That's how this calculation should work. And this is the ancillary qubit that allows you to do this operation. Anyway, that's basically what I said. And this is the critical point. These two are really the critical points, encoding and then ancillary qubits, which are new techniques you have to learn or talk to the experts and they'll explain to you. Okay, so here's a simple example. So again, I'm still doing, as I mentioned at the beginning, baby steps, okay, if you want. This is still the one-dimensional Poisson. This is the force vector chosen more or less at random. This is the quantum solution, are the red dots, and this is the exact solution. You can see you can solve them. You get the solution. You don't get something else crazy. You get the solution that you want. Okay. Good. And now do you gain anything? And this is the critical point. Here's where, okay, there should be a drum beat here. So first of all, we're making approximations. The polynomial encoding approximates the vector of either polynomials. Then you discretize the domain. Okay? That's the method converge in the sense of a numerical method. So we are in the business of formulating converging or convergent numerical methods. And you can see that this solution that I showed here, okay, incurs some error, but the error goes to 0 at a predictable rate when you increase the resolution of the problem, as you would expect. Okay. And finally, if you measure complexity, you find that the complexity as a function of the size of the problem, okay, so this would be 300 elements, okay, is polynomial, is logarithmic. Okay, the complexity is logarithmic, okay, both for the rotation gates and for the CNOT gates. This is how you measure basically the computational cost in these problems. So this is a big deal. This is a huge, huge deal. Okay, if it works in general. Okay. If it only worked for this problem, it would not be a huge deal. But if it worked in general, it would really be a huge deal, because typically the best you can get with fast Fourier transform is n log n, and so on. So this really beats any classical formulation of the problem by a lot, because it's not a polynomial, it's not a power law kind of acceleration is an exponential acceleration. That's very big. Okay, anytime you have anything exponential, that's huge game changer. Okay, so 2D Poisson scaling, the same thing. Okay, so this is the same thing, but not in 2D. Okay, so it requires a bit more coding. This is the force function that we use. This is the displacements that we got from the quantum computer. Well, this is using an emulator with a WizKit. There's an exact quantum computation, no errors. And again, in 2 dimensions, we get logarithmic scaling. So again, that's a big deal. So that makes you salivate. It's a computational mechanician. But you see a way here, a way to really do problems you couldn't solve, you couldn't do before. Like for instance, Fe squared. Okay, so Fe squared. Okay, so very often you want to do maybe a composite. So at every quadrature point in a finite element mesh, because you have a representative volume element that you use to compute the effective response of the element, and that's what you pass to the upper scale. So this typical scheme for doing 2-scale calculations called Fe squared in the business, and that's basically what it is. It's called Fe squared because the RV itself is also discretized into finite elements. And okay, so the idea here, the winning idea would be to say, well, now we have something where we can use at least a regular grids with exponential acceleration. Fe squared is impossible. So why don't we do the RV calculations using quantum computers? And we provide the exponential acceleration that would make Fe squared feasible on demand. Okay. Yeah. So of course, what you can do is to take these kind of problems, and you can reduce them by introducing an equivalent linear solid, as it's called, okay, in the trade. Plus the fast Fourier transform, you can reduce these kind of problems to a sequence, an iterative solver at which in every iteration you're solving a Poisson-like problem, the type that I described earlier. So now we would solve these problems basically by throwing the residual to the right-hand side and solving the problem for the equivalent linear solid. That's kind of a Poisson problem, okay? So now the code that we developed earlier can be applied for these problems also, but you have to iterate to eliminate the residual. Okay, well, so we've done problems of this type, okay? So for instance, at this level, you would be interested in evaluating the behavior, the evolution of very large numbers of dislocations. These are elastic defects. Okay, so these are the kind of problems that we have solved in 2 dimensions. Again, baby versions of the problem where you assume anti-plane shear, screw dislocations. Okay, you introduce on input, when the input to the computation would be the remote stress you're applying to the RVE, and the output would be the pitch scale of forces on each one of the dislocations. So that's what gives you dynamics. Okay. Well, so again, you can reduce this to a sequence of Poisson problems, and at the end of the day, you get again logarithmic speed up. So now you can take paradise right away and replace it by a quantum version that really is workable, okay, on demand. Okay, it gives you something that's exponentially faster for large n. Another example now would be, for instance, how to deal with polycrystals. Okay, so again, we've done very idealized versions of this problem. Now in anti-plane shear, small strains, you have it. So here, the input to the problem would be the average strain for the RV. The output would be a measurement of average stress. Here, I need to say something, which is the way you get information out of the calculations is by measurements. Once you measure a state, you destroy it. It's over. Inside. That's quantum mechanics, nothing you can do. So if you wanted every single displacement of every node in the RVE, you would need nothing. Fortunately, the nature of these calculations is that you only want the average, bless you, the average stress, because you only need to measure 6 numbers. Okay. So that means that the measurement is not It's not a huge operation, it's a small operation, and that's in the nature of this problem. So that's why these RV problems are really suited for quantum computing, because also at the end of the day, you only need a very small number of numbers, okay, so the average stresses. So the measurement part of it is actually trivial. Okay, and again, so we've done things like this, okay, where we use the method of Moulinex and Suke, where you reduce these problems to a sequence of Poisson-like problems. We use our Poisson solver, and at the end of the day, you get an algorithm. So now we have how many? 4 problems where we have logarithmic scaling. So it seems that we're onto something here. Okay, and well, that's basically what we've done so far. As you can see, very idealized problems, but they point into the very potential payoff. So to summarize basically the state of affairs, say you want to solve RV calculations, and if you use finite elements, you could get, well, depending on how you do it, order n squared, okay, but very slow calculations. If you use fast Fourier transform, because you have now a regular grid, and you can apply the fast Fourier transform, you get order n log n. Multi-grid, you can reduce this to order n, but now quantum computing beats them all by a lot. This logarithm, okay, this exponential acceleration. Now for small n, it's not clear, okay, so it could go either way, depends on the day or the week, basically. But for large n, the potential payoff is huge. It's really a game changer, okay? And that's basically where we are. It's good because we're running out of time. And okay, so if you want to program these computers, you have to learn how to think a bit differently. Okay, you have to understand how this not all of quantum computing, which is a huge field, but how these particular quantum systems actually work. Okay. So if you miss something in the presentation, don't feel bad, because according to Richard Feynman, I think it is safe to say that no one understands quantum mechanics. Okay, so he's probably right at some level. Okay, he was very provocative. His statements got him in trouble a lot of times. But I think, okay, no one understands quantum mechanics fully, perhaps. Okay, but at the level of these quantum computers, I think we understand enough. I think that we can draw some conclusions. Okay, so the conclusion is that the reason why quantum computing is different and is potentially advantageous is for a number of reasons that are peculiar to the systems. You have quantum entanglement, the fact that you can span very large vectors, you can 2 to the n instead of 2 times n, which you would have if you didn't have tensorial algebra. If you were a linear algebra, it would be 2n, but because they combine tensorial, you have 2 to the n. Okay, quantum superposition is basically related to the same thing, the ability to represent vectors of very, very high dimension. Okay, in quantum parallelism, this is the connection with analog computers that I referred earlier. Because once you apply a unitary operator, it gets applied to the entire system all at once. It's like inflating the membrane. Apply the pressure, the entire membrane gets inflated. Okay, and then you can get exponential speed up for some problems, not for all of them. Okay, so the trick is to identify the problems in computational mechanics where quantum mechanics, the quantum computer, really adds a game-changing advantage. Okay, what is known sometimes as quantum supremacy. Okay, and the operations are unitary, meaning you need new algorithms. So the way you would solve structure, okay, forget about Cholesky, okay, you would have to really redo the thing from the beginning, but the payoff is potentially not that it's worth doing it, because that's the point. Now, IBM now has a computer of 433. I think that's the maximum they got to. So that's, okay, 2 to the 1,000 is more than the number of atoms you have in the universe. So it's a completely unthinkable size, okay? And there, I saw some discussion about going to a million qubit computers, that of course is absolutely, you cannot wrap your mind around something like that. I mean, it's something unthinkable, okay? And there are any number of emerging facilities worldwide, for instance, the Amazon Caltech hub at Caltech, UK hub, BSc, okay? So we're very fortunate here that we have BSc that provide facilities available to everyone who wants or needs to code these quantum computers. So they're building an actual device that is supposed to be available next year. They're working with a company called Kilimanjaro. They're using superconducting cryogenics, which is a very standard, almost commercial type of device. And there is a program in Spain, actually. I wanted to mention this because I think it's very exciting. Okay, Quantum Spain, within this program. So BSc has commissioned, if you want, okay, the building of this device, and it will be really a wonderful device to have available to this community, okay, and to other communities. And this is what they promise now that, oh, okay, they'll get to 30 qubits. I thought 25, but it keeps getting better. There's 30 qubits by the end of 2025, and they have huge expertise. So I don't know if you know that, but it's the quantic group. Are there any quantic people here? Okay. I mean, these people really know what they're doing. Okay, so as computational mechanicians, we would have to work with them as a team. We provide the application, the knowledge about the application. They would provide the expertise at actually developing these kind of codes and managing these kind of computers in an effective way, which is not entirely trivial. So many opportunities remain. Okay, so of course we would like our RVs to be physically realistic. We would like them to be three-dimensional, involve things like plasticity, you name it. Okay, dynamics is very natural for us and for quantum computers both, because basically the propagator for dynamics is automatically unitary. You have a structure, you can define the Hamiltonian of the structure. This is the propagator for the structure that generates a group of transformations, and the propagator itself is unitary. So this fits very nicely. Dynamics fits very nicely in quantum computers. So that's an opportunity. When you do data-driven calculations, very often or almost always, you have to do very large searches, very large databases. You can do also unstructured searches in quantum computers. Grover's algorithm is the most basic one. Here you have polynomial speedup. It's not exponential, but okay, everything helps. Okay. If you have 1,000,000 data points, you can search them in the same time as 1,000 data points in a classical computer. Get us quite game. And the question is, you know, to quote my colleague at Caltech, is it possible to achieve quantum supremacy? So, I mean, for certain problems, solve certain problems you cannot solve classically. Okay, and there are many challenges: hardware technology, decoherence, and error correction. Fortunately, it's very difficult to control the qubits, so you have to compensate for errors, and then develop new quantum algorithms. And going back to Feynman. Nobody said it was going to be easy, but perhaps the challenge is attractive in and of itself. Okay, and with this, I'll thank you.
Thank you very much, Michael, for this wonderful thing. We've got a few minutes for questions, so hopefully to go.
The quantum people are going to start throwing things.
I'm sure that we
Tell me all the things that were wrong.
Don't be shy. I'm sure that some of you want some questions.
When you said zero computing time, was it simple statement or?
Well, I was thinking of the, so for instance, the membrane analogy, right? You apply the pressure instantaneously, the force instantaneously. and you get a solution.
But there is a physical process behind it. So this one takes time, right?
Basically zero. Okay, let's see.
Okay, because it can take time depending on the physics behind.
Yes, yes,
And
yes.
speeding up this process,
Absolutely.
computation is another problem which could be.
So you don't want an analogy to another set of physics that is slower than the one you have. Okay.
Exactly. That's the point.
Yes.
So basically,
Sure.
you aiming to, you suggested that we could have unstructured meshes for the coarse
Yes.
scale and
Exactly. And structure for the algorithm. That's, you got it. You're so clever.
We seem to have a question online from Elmira Biran. Elmira?
Yeah, can you hear me?
Yes, we can hear.
Yeah. Okay, great. Thank you. So thanks a lot for the presentation. My question, the first question is about the theory that you presented, that we have this wave vector. So if I assume it at the scale of continuum mechanics, so I'm going to consider that for a material point, each point has a wave vector in n-dimensional,
Yes.
right?
Yes, yes.
All right. So this mindset will be applicable at the scale of the quantum, also at the scale of DFT.
Well, what you would like is to update all material points at once. Okay? We don't know how to do that yet, okay? But I think we're pretty close. And that's
Alright.
how you would make, I mean, really the approaching tremendous. Okay, if you could actually, as is typical, if you could entangle all the material points and update them all at once,
I
that would
see.
be absolutely great.
All right. And the second question is about the validation of the results. So if I understood it correctly, you have compared the results of the quantum algorithms with analytical results. If we have a model that's very large and three-dimensional, what do you recommend for validation of the results?
Well, I mean, that's standard, right? I mean, we're in computational mechanics, we do that all the time. Okay, we have solution algorithms, approximation techniques, and we know how to measure errors and error plots and make sure that the algorithm, the approximation scheme converges in a proper way. So that's not different from a classical computer. It's just that.
All right.
Yeah.
Okay, checking the error. Okay, thank you.
Thank you. Can I ask you something, Miguel? Is it,
Sure.
obviously, you know, the applications that you were showing were very specific, and you still started with a finite element mesh. So it seemed to me that you were using two types of computers,
Yes,
a traditional
yes,
computer and a
Absolutely.
quantum computer.
We were talking about that.
How does that, so how do they connect? Is that connection effective? Would you lose all the gains?
That is a question for Arthur. Yeah, so they're either they're thinking about it or they're doing it already. Because using a supercomputer for the, say, the top calculation, finite element calculation, and then the calculations you do at the lower level and on the quantum computer. It's not clear exactly how to me. It's not exactly clear to me how to implement this in practice, but that's because it's a research area. Okay?
But that's what you see. We would have to.
Yes,
You don't
yes,
see
yes.
a world or a time where everything can be done in the quantum computer with a finite element mesh, and somehow not need the traditional computer.
I can only see so far in advance. Okay, I mean, if you could do this, okay, classical for the microscopic, quantum for the microscopic, that would be tremendous. Beyond that, I don't know.
Okay.
Yeah, but I don't think so. I think we were talking about this. I mean, quantum computers are not good for any problem, for every problem. You can choose very carefully. Yeah.
Okay. So the possibility of combining them makes it quite interesting. Okay. Any further questions? Yeah.
Yeah, I have two questions. So the first one is like this second paper. I'm not versed in computational mechanics. This is the second paper I see in computational mechanics on quantum computers.
Yes.
And the first one was I think that 1 year ago, 2 years ago by Google on simulating spring networks.
Yes.
Yeah, I don't know if you're aware of that paper. And so what
Sure.
like there is some connection between these two works.
Well, what I've seen typically so far is that, okay, people will take a conventional calculation, classical calculation, and take one part of it. So for instance, the linear solver, the linear equation solver, and pass that to quantum computer. There you get some acceleration, but the remainder of the calculation remains classical, and that's the bottleneck. So in the end, you gain nothing. So that's what I've seen. It's out there. I mean, it's the easy thing to do, where you take a calculation, you change one solver by another, and then you can submit that for publication. The real trick is for all the calculation from beginning to end to have logarithmic complexity.
Yeah, but
All of it,
but I
without
think-
any bottlenecks.
I think that's not what they did in that paper. Like what you, I think what you're referring is what's called hybrid quantum computing, where you accelerate the solver basically in the quantum. No, right. But I think that they did this like in that. I don't know. They accelerate like they simulated the full spring network and they got some results from that. I think they just. I haven't read that paper.
I'm not sure they get logarithmic and scaling for the entire calculation.
Okay.
So the state preparation, the measurement, everything. Okay.
Mhm.
I haven't seen any other paper
Okay.
that does that, because it's very early days. Okay, so I think people, of course, will learn how to do these things. I think it's a growth area. So somebody has to voice the alarm, and then I think the subject will grow tremendously. We'll learn about these things.
Okay.
But to me, it is critical not only to have convergence, obviously, that's what you're saying, but for all of it to be scalable.
Sure.
And I haven't seen that. So.
Yeah, my second question is more like, a lot of the algorithms that have been shown to have some kind of exponential. So actually, exponential speed on quantum computers is a kind of rare. So it's not easy to have exponential speed. And usually, many times when we have found it, there have appeared some quantum-inspired classical methods that have disproved that you have quantum supremacy. So, like this has happened a lot of times to IBM and to Google, mainly when you have approximate calculations. So the question is like, what kind of robustness you think is your method against classically quantum-inspired methods?
I think it's unitarity. Your problem has to be as close enough as unitary as possible. I think it's actually a theorem that the fast Fourier transform cannot be executed faster than n log n. Okay, so doing the same thing at log n, that's the winner. Okay. So that's absolutely clear. You cannot do it classically. Classically would be n log n. You cannot do better with the fast Fourier transform. Maybe you say, okay, you can replace the fast Fourier transform by something else. Perhaps.
There is actually, like it was shown 1 year ago that you can approximately simulate quantum Fourier transform, but approximately in linear time. Yeah, so it's you have like it actually.
Linear. You're
Yeah.
still not there.
Yeah,
You're still not long.
exactly. Yeah, completely.
Yeah, no, but you're right. There's this race between classical and quantum. They're trying to outdo each other. And I think
So what
losing
protects you?
proposition for the
Yeah.
classical side. Yeah.
So what protects you right now from classical simulation basically is the quantum rings in your algorithm.
Absolutely. And that's quintessentially quantum.
Yeah.
Okay, well, one final question. Oh, sorry, there's another question online. Sorry, I haven't seen that hand. Sahid?
Hi, can you hear me?
Yes, we can hear you.
Thank you for the talk, Professor Ortiz. I have a question about this verification that you showed for the 1D Poisson problem, where you compare analytical with the quantum solution, because you said that you cannot extract the displacement at every point, you only get average things. So how do you get this solution in this graph that you compare?
Well,
The
because
dots,
we
red dots.
absolutely wanted to show the displacement field everywhere, so we had to do a lot of measurements. Of course, that would be a losing proposition in general. That's why the RV is especially good, because you only need to do 6 measurements, okay, out of a system that maybe has millions of degrees of freedom, okay? But there we just wanted to show the dots, every single dot, so we had to do lots of measurements. If you really have to do that, then forget it. I mean, you're not accomplishing anything, okay? That was just to compare the two curves specifically for that.
It was just a validation.
Validation. Yeah.
But you have negative values for u in that graph because from measurements you only get like absolute square value, which should always be positive. So how are these negative values coming?
No, you can measure basically anything. You can take any projection. This is not true. So, I mean, as far as I understand, maybe I have to can explain it better.
Probabilities are positive, but the numbers can be negative.
Exactly. Yes.
Okay, well, thank you very much. Unless there's any final questions, I think, thank again our speaker. Thank you very much.
Still on there?
Yes.